Okay, so today I want to just say a couple more words about linear programming, and then we're going to move into a special case of linear programming known as maximum flow. So I just wanted to make two observations. One is concerning duality, and the other is concerning different ways of representing the linear program. So let me first say the thing I wanted to say about duality. So duality, we saw just by construction that the opt of the primal is at most the opt of the dual. Right, where the primal looked like max C transpose X subject to AX is at most B, and the dual looked like min B transpose Y subject to A transpose Y is equal to C, and Y is at least 0. Coordinate-wise. So just by the way we motivated and defined the dual, we saw that immediately we had what's known as weak duality. The opt of the primal is at most the opt of the dual. And I did mention that there's something called strong duality, which is not going to be covered in class. The proof of it's not going to be covered in class. But what it says is that if the primal is feasible and bounded, then so is the dual, and their optima are actually equal. What about the cases when the primal is actually not bounded? So for example, max C transpose X subject to no constraints. Then you can send C transpose X to infinity, right? Because it's an unbounded polytope or polygon. So since you know that any solution to the dual is an upper bound on solutions to the primal, what does that say? If the primal can get arbitrarily large, what should that say about the dual? Well, it should say the dual is infeasible, that there is no solution to the dual. Because if there had been a solution to the dual, that solution to the dual would give you an upper bound on the best you can do for the primal, but there is no upper bound because the primal is unbounded. Okay? So there are consequences too, like as follows, that the primal is unbounded, meaning the opt is infinity, implies that the dual is infeasible. And you can also show that, likewise, if the dual is unbounded, that implies that the primal is infeasible. So that's just one thing I wanted to point out about duality. And the other thing I wanted to point out is, when I first introduced linear programming, I said that the input looks like C transpose X, just like the primal there, such that AX is at most B coordinate-wise. But you might, in general, you might want to have some kind of optimization where so max C transpose X. You might want to have some optimization max C transpose X, but not all your inequalities are less than or equal to. Maybe you want to have some greater than or equal to inequalities. Maybe you want to have some equality constraints. Okay, how do you do? So for example, when I talked about simplex, I said simplex expects its input to look like max C transpose X, subject to AX equals B, and X is at least 0 coordinate-wise. So this is a different format for specifying an LP. And you could ask, are these different problems? Is one of these? Can you, any LP that's expressed this way, can it also be expressed this way, and vice versa, right? So I could call this LP, LP problem type A and LP problem type B. Are they really different problems, or are they the same problem? And what I want to convince you of is that they're actually the same problem up to maybe increasing the number of variables by a factor of 2 and maybe increasing the number of constraints by a factor of 2. Other than minor changes by constant factors in the number of variables and constraints, one format for representing LPs can express the other format. Okay? So these two formats are actually equivalent. Let's call this format alpha and format beta. Okay? So why are they equivalent? I'll show you that you can represent alpha LPs by beta type LPs and vice versa. So using alpha to represent betas. So let's say we had an LP of this form. Okay? How could we represent that as an LP of this form? Well, we'll still say, look, max C transpose X, that's already in the right format. And then we have all these constraints. So AX is a vector, right? Where AX basically is a vector that looks like, here we have the sum over I of A1i xi is at most is equal to bi, or B1. Sum of A2i xi is equal to B2. Sum of A3i xi is equal to B3, etc. Right? That's what AX is. AX equals B. AX equals B is a bunch of equality constraints that looks like this. Right? Let's say that A has m rows. Sum of AMI xi equals BM. Right? So AX equals B, if A is an m by n matrix, is m constraints, m equality constraints that look like this. Right? This is the first row of AX. This is the second row of AX, the second entry in AX, the third entry in AX, etc. AX is a vector that has m entries. These are the m entries of AX. And we're saying that all of those have to equal the corresponding entries in B. Now, if I'm only allowed to use less than or equal to constraints, notice that, if you say that x equals y, that's the same thing as saying x is at most y, right? And also x is at least y. But x is at least y is the same thing as saying minus x is at most minus y. Right? So x equals y is equivalent to these two constraints. So I could just do that. I could say, basically double every one of these constraints to be two constraints. So one constraint will be the sum of A1i xi is at most B1, and also the sum of A1i xi is at most minus B1, where I have a minus AI here, minus A1i here. So every constraint just gets doubled. Okay? And then similarly, this x is at least 0. What does that mean? It means that minus x is at most 0. So it means I also have the constraints minus x1 is at most 0, minus x2 is at most 0, all the way down to minus xn is at most 0. Okay? So now I do have an LP of this form, max C transpose X, subject to a bunch of linear things being at most something on the right-hand side. So I've represented this as that. Okay? So that says that I can use alpha-type LPs to represent beta-type LPs, and I've at most doubled the number of constraints. And going in the other direction, how can I use... Oh, whoa, that stayed there for a while. How can I use beta-type LPs to represent alpha-type LPs? So we can define these so-called slack variables. I mentioned this last time when I talked about simplex. Just define SI to be BI minus AXI. Okay? We know that BI minus AXI is non-negative, so we know that all the SIs should be non-negative. And then now we have the constraint that we want basically, if we want to represent it like this, I could say max C transpose X subject to. Now, in beta-type LPs, all the variables have to be non-negative. But so far, only these SIs are non-negative, right? These SIs are just more XIs. I basically just increased the number of variables. I used to have n variables, x1 up to xn. Now I have m plus n variables. I have x1 up to xn, and then I have s1 up to sm, because I have an SI for each constraint here. So in beta-type LPs, all the variables have to be non-negative. But in alpha-type LPs, but what we said here is that only the S's are non-negative. How can I make sure that all the variables are non-negative? I can basically just double the variables. For each variable xi, I can introduce two new variables. I can write that xi is actually equal to x plus I minus x minus I. Does that make sense? Any number, whether positive or negative or 0, can be written as the difference of two non-negative numbers, right? 5 can be written as 5 minus 0. Negative 5 can be written as 0 minus 5, right? Any number can be written as the difference of two non-negative numbers. So that's what I'll do. I'll just double the number of variables, and then I'll have a constraint. I'll have constraints that say xi plus has to be at least 0, and xi minus has to be at least 0. So my constraints now look like, I'll have basically A11 x1 plus minus A11 x1 minus plus A12 x2 plus minus A12 x2 minus plus S1 is equal to B1. A21 x1 plus minus A21 x1 minus plus A22 x2 plus minus A22 x2 minus plus S2 is equal to B2, etc. And then I'll say all these variables have to be non-negative. So for all I, xi plus and xi minus both have to be non-negative, and also for all constraints j, sj has to be non-negative. Right? So this is an LP of type beta. So I've represented my type alpha LP as a type beta LP by introducing all these so-called slack variables si, which is just the difference between bi and axi, and also for each original variable doubling it, right? And basically writing every variable as the difference of two non-negative things. And then now I have only equality constraints, and I have that every variable has to be non-negative. So these two, up to possibly doubling the number of constraints in variables, these two LPs are equivalent in terms of expressive power. Okay. Anything you might want to represent in one, you can also represent in the other without increasing the LP size by that much. So that's something just to keep in mind. And I should say beta-type LPs are what's called standard form LPs. That's just some jargon. Okay, so good. Now I want to move into a special case of LP called max flow. I'll define the problem for you. I'll show you an algorithm. I'll prove to you that the algorithm works, and I'll cover max flow both this lecture and on Thursday's lecture. Only the stuff I say today is fair game for midterm 2. Anything I say on Thursday is not fair game. But basically, for the midterm, you should know what flow is, what network flow is. You should know that there is an algorithm for it and that it has a certain runtime. Okay, and you might not need to know all the details of certain proofs that will appear Thursday, but you should at least know the main statements that I'm going to cover today. Okay, so today we're going to be mostly covering network flow. So what's the idea for network flow? So imagine the following setup. Okay, we have a graph where the edges in the graph represent physical pipes. Okay, and water can flow through these pipes. And vertices represent junctures where pipes meet. Okay, so there's some vertex. Here's another vertex. Here's another vertex. Here's another one. There's some pipe that flows. And by the way, edges here are directed. So there's some pipe that flows, let's say, in this direction. There's another pipe that's allowed to flow water in this direction, and as well as here. And let's say there are also some pipes here. Okay. So normally I just draw edges as lines. Here I drew them as pipes, okay, just to be suggestive. And two of the vertices are actually special. Let's say two special vertices. S is the so-called source, and T is the sink. Let's say here this is T and this is S. And the idea is S is a faucet. S has a faucet where there's an infinite supply of water over here on the S side. And T is a drain. So an infinite amount of water is allowed to drain at T. For all the other vertices, water can flow into them and water can flow out of them. Okay? And these pipes, let's say, have different capacities. They have different diameters. So some pipes support more volume per second, let's say, of water than others. Okay? So for example, maybe this pipe here supports 20 liters per second, as does this one, as does this one, and these only support 10. Okay? So now that you get the idea that these edges are pipes, let me draw this in the standard way I draw graphs, which is just that edges are single arrows. Okay. So actually, let's just redraw this. So I said 20, 20, 20, 10, and 10, and this is S and T, and this is A and B. Okay. So these numbers that I drew on the edges, on the pipes, represent the capacity. Okay. Capacities are non-negative numbers. So each edge, E, has a capacity UE, which is non-negative. And what I'd like to do is I'd like to understand what's the maximum rate in volumes per second that I can push water from this faucet, from this source S, to this sink T, where the water flow has to obey the capacity constraints. So for example, I could choose to push water this way, right? And notice that you can think that if there's some pipe along the path that has lower capacity, that's a bottleneck for the rest of the path, right? All these pipes along this route have capacity 20, right? So I can route 20 liters per second along this path, right? But a better thing to do would be, let's take that same graph. A better thing to do would be, let's say, route 10 this way, route 10 this way, and then route 10 also this way. Okay? And you can verify that this routing does satisfy the capacity constraints. Because on this edge here, I'm routing a total of 20 liters per second, but this has capacity 20. I'm just rewriting the amount on the path, along the path. And similarly here, I only have capacity 10, but I'm only routing 10. Going down, I actually have capacity 20, but I'm choosing to only use 10 of it. That's okay. I'm not exceeding the capacity at least. And here I'm using capacity 10. Here I'm using capacity 20. I have capacity 10. I have capacity 20. Okay, so I'm not violating any of my capacity constraints. Okay? So this has total flow. This flow has total flow, or value 20. This here has value 30. The value of this flow is 30. So this is better, and this turns out to actually be the maximum flow that you can route in this graph. So this is the max flow. And that's what we like to find. Given a directed graph with capacities on edges, calculate the max, find the max flow, and tell me what its value is. Okay. So let me now properly define what a flow is. So what is a flow? Okay. A flow is just a vector which is m-dimensional, right? Where m, I always use m to denote the number of edges in a graph, and n is the number of vertices in a graph. So it's an m-dimensional vector. Basically, it assigns a value to each edge, which is the amount of water you're flowing on that edge. So f at this edge is 10, right? F at this edge is 20 because I'm sending, this path is sending 10, but I'm also sending another 10. So that f on that edge is 20. And also, for all e edges in the graph, f sub e has to be at least 0. I'm not allowed to flow negative water. And it's called a feasible flow if for all E, I also have that Fe is at most the capacity. I'm not allowed to flow more than the capacity. And then there's one more other thing that I want to say about what is a valid flow. So this says that I obey my capacity constraints. Another thing that should be true about a flow, a valid flow, is that, so yes, S is an infinite source and T is an infinite drain. But if you look at any other vertices in the graph, they are not sources of water, right? There's no water that originates at A. The only water that touches A is the water that comes into A. And whatever water comes into A had better leave A, because A is not a drain either. So there's conservation of flow, which says that for all vertices V in the vertex set other than S and T, the amount of flow into V is equal to the amount of flow out of V. The sum over all edges of the form something comma V, this is the edges flowing into V of Fe, has to be equal to the sum over all edges of the form V comma something of Fe. Okay? And this is conservation of flow. Okay? So whenever we talk about a flow vector, a valid or a feasible flow vector, we're talking about a vector in Rm, all the entries are non-negative, it obeys capacity constraints, and conservation of flow is met. And what's the value of a flow? We'll see that there are many equivalent definitions soon, but one way to define the value of a flow, the definition that I'll give is that the value of a flow is just defined to be the total water that leaves the source. So it's the sum over all edges E that look like the source going to somewhere of F sub E. And the max flow problem, max flow is find a flow, a feasible flow F of max possible value. Okay. So what might an algorithm look like to find the max flow? Well, a natural algorithm is a greedy algorithm, right? So you're given the graph with capacities. Find some path from S to T. How can I find a path from S to T? Use depth first search, use breadth first search, right? We know how to find paths in graphs. Find some flow from S to T. That's a sequence of edges or a sequence of pipes. Those pipes, those edges might have different capacities. Look at what the bottleneck edge is on that path. Namely, on that path, look at the edge that has the least capacity and send that amount of water. Okay? That's guaranteed to saturate at least one edge, right? Namely, the edge that was the bottleneck. After you've done this, it has no capacity left. You've filled it up. And then just iterate until you can't find a path anymore. Until there's no more ST path. DFS fails to find an ST path. This algorithm definitely terminates, right? Because every time you run one iteration, the number of edges in the graph shrinks by at least one. Because there's that bottleneck edge, which now has no more capacity left, so it's gone for the future. And there might be many edges that had the same capacity as that bottleneck edge that are all going to be gone. But at least one edge will certainly be gone. So there's a natural greedy algorithm. It's, we can bound its runtime. Its runtime, we said there are most m iterations, because each time you iterate, one edge will disappear. And each one is a DFS. DFS takes linear time. So the total runtime is O of m times m plus n. M DFSs, each DFS takes m plus n time. The problem is that this algorithm is wrong. It's an incorrect algorithm. Why? That same graph we just drew right, so I said 20, 20, this is 10, 20, 20, 10. Maybe, who knows what path DFS will find? Maybe the first thing it'll find is this path. The bottleneck on that path is 20, so it'll send 20 units of flow. And then now it removes all the edges that are fully saturated. What's left? What's left is this graph. So now we still have this edge with capacity 10, we still have this edge with capacity 10, but all the other edges, the three other edges are gone because they got fully saturated. So now we try to find an ST path using DFS in this graph. There is no ST path. So we halt, we terminate, and we say we're done. There's no more way to push any more flow. But we're now left with a flow of value 20, whereas we know that the max flow in this graph is actually 30, has value 30. So this has failed to find a correct maximum flow. So unfortunately, this algorithm is a wrong algorithm. Incorrect algorithm. Okay. So let's fix it. And the fix will be another greedy algorithm that's just does a little bit more work, called the Ford-Fulkerson algorithm. And before I give that algorithm, I do want to point out that, yes, max flow is a special case of linear programming. Right? So we already know an algorithm to solve max flow correctly. Namely, use any algorithm for LP. So use simplex. Okay, simplex is not in general a polynomial time algorithm, but I did mention that there are polynomial time algorithms like the ellipsoid algorithm and like the interior point method. So use one of those. That's a polynomial time algorithm. Those are more complicated, though, so I want to show you an algorithm that's not as complicated. But first, let me just show you why it's an LP. You could say, look, max over f, right? Max the sum over all edges of the form s going to somewhere of fe, right? That looks a lot like C transpose x, right? Namely, the C vector is a bunch of ones and zeros. The C vector has ones these are the variables, right? F is the x. F is the x vector over there. So all the entries of F corresponding to edges that leave S, they have a coefficient of 1. So C is 1 there. And all the other edges that aren't out of S, they have a coefficient of 0. That's why they're not appearing in this sum. So this is exactly the form C transpose X, subject to certain constraints. Subject to, for all E, FE is at most UE, so that looks exactly like an inequality constraint there. And also FE is at least 0, but that's the same thing as minus FE is at most 0. Right? And then the conservation of flow, I can write that as also for all vertices V, which are not S and T, I have that the sum of E looking like star V of FE minus the sum of E looking like V star of FE is equal to 0, which is the same thing that as it's at most 0, and its negation is also at most 0. Right? Again, I can represent, we already saw this, I can represent equality constraints as 2 inequality constraints. Okay? So this is exactly a type, an alpha type LP. Right? So, bam, now just plug that into an LP solver. But I don't want to do that. I want to actually show you an algorithm from first principles that's Taylor designed from the max flow problem. So this is going to be called this is an algorithm called the Ford-Fulkerson algorithm, which I believe is from 1956. It's definitely from the 50s. Okay. First, what I want to say is this is going to be useful for notational reasons. Whenever I have an edge in the graph, E, I might not necessarily have the reverse edge. Remember, this is a directed graph. But I'll pretend that I do have the reverse edge. I do have the reverse edge. And I'll pretend that I have it with capacity 0. I mean, that can't hurt me, right? Not having the edge is basically the same as having it with capacity 0. Because if it has capacity 0, it basically means I can't use it. So it's like it's not there. So, but it'll be notationally convenient for what I'll say next. For each edge E in the graph, I'll pretend that the reverse of E is also in the graph with capacity 0. It might have already been in the graph, right? It might be the case that both E and the reverse were in the graph. If so, that's fine. I'll just leave them with the capacities they already had. But if the reverse of E was not in the graph, then I'll pretend that it is there with capacity 0. And also, we'll pretend that the flow on the reverse of E is just equal to minus the flow on E. So, in truth, the actual flow vector is a non-negative vector that only has entries corresponding to the edges in the graph. But I'll pretend that there are these shadow edges, which are these reverse edges that are also there, and just it'll be notationally convenient to say that whenever I choose to put some flow on E, it's basically like I'm putting negative that flow on the reverse of E. Okay. Or if rev E, and similarly, if I choose to put some flow on the reverse of E, it's like I'm putting negative that on the original edge. And then I'll define the residual capacity given a flow. That flow implies a residual capacity on the edges, where the residual capacity will be UE minus FE on each edge in the graph, including the reverse edges. Okay? So what does this mean? So pretend that I had some edge that has capacity 20, and then I chose to put 20 flow on that edge, so I've used up all the capacity. Okay? What does this mean for the reverse edge? The reverse edge has capacity 0, and it has flow negative 20. What's the residual capacity? What's the residual capacity of the reverse edge? It's its capacity, which is 0, minus its flow, which is negative 20. So it's 0 minus negative 20, which is 20. So from the perspective of the residual, there is flow on this reverse edge. Okay? What does that really mean? It means that I'm allowed to push on the reverse edge, push water on the reverse edge, which really means I'm allowed to undo some of the water on the normal edge. Right? Because the normal edge is currently pushing 20 liters per second. What I'm saying is I'm allowed to undo up to 20 liters per second, okay, because the residual edge has positive capacity. Okay? And this defines a residual graph. Which I'll call GF. So what's the residual graph? It's a graph on the same vertex set, and it includes all the edges and possibly reverse edges that have positive residual capacity. And the capacity you write down in the residual graph is the residual capacity. And what the Ford-Fulkerson algorithm is you start off with the 0 flow as your current flow, and you just iteratively form the residual graph for your current flow. Right? The residual graph for the 0 flow is the original graph. You find an ST path in the residual graph, and then you add it into your flow. And then again, you iterate. Now you find a new residual graph. You find an ST path in that. You add it to your flow. Now you have a new residual graph. And you just keep greedily trying to find paths, not in the original graph, which is what we tried first, which didn't work, but we iteratively keep trying to find paths in the residual graph. So let's run through an example. And let's do that same exact graph there. So this is S and T, A and B, and these are my edges. I said 20, 20, 20, and 10, 10. Okay? So right now my current flow is the 0 vector. And this graph, G, is the residual graph for the 0 vector. I'll do a DFS. I'll find an ST path. And maybe I find this. The bottleneck on this has capacity 20, so I'll push 20. Okay. And then now I go to the next iteration. Okay. What does that graph look like? What is the new residual? So now the new flow looks like this. Right, I'm pushing 20 along that path. That's the new flow. What's the residual graph for this flow? So actually, in the residual graph, I've exhausted all 20 capacity on this forward edge, so the reverse edge has capacity 20. Similarly, I've exhausted all 20 flow going down here, so the reverse edge has capacity 20. And the same thing here. This has capacity 20. So this has capacity 20, 20, 20, and then 10, 10. now I find an ST path here. Okay. I think there's only one way to get from S to T here, which is you do this. The bottleneck on this is any one of these two edges. They have capacity 10, whereas this has capacity 20. So the bottleneck is 10, so I'm allowed to push 10 units of flow on this path. Okay. And then now I add that 10 units of flow to this here. Notice that before I was pushing 20 all along this path, I was pushing 20 down. Now I've chosen to push 10 up on the reverse edge, which is the same thing as reducing the amount of flow going down by 10. So instead of pushing 20 down, now I'm only pushing 10 down. Because I used to push 20 down, but now I decided to undo 10 of it by pushing up. So now I'm only pushing 10 down. So now the new flow looks like this. So here I'm pushing 10, 20, and 20. And I'm also pushing 10 and 10 here. So I'm also pushing 10 here and 10 here. Okay? Let me draw that as my directions. So this 20 gets split up into 10, 10. And this 10 and this 10 come together to meet and make 20. So what's the residual graph here? So this edge is fully exhausted. So now it points in the reverse direction with 20. Here I'm pushing down 10, which means I still have 10 left in the down direction, because this has total capacity 20. This edge has total capacity 20, right? But I'm pushing 10 right now, so it still has 10 left. And it also has 10 left it also has 10 capacity in the reverse direction, right? So what that looks like is I have. Sorry, we're in the middle of a lecture. So we have 10 capacity going down this way and 10 going this way. And we have 10 going backward this way. All this 20 is being used, so we have 20 going this way. And all of this 10 is being used, so we have 10 going this way. That's the reverse edge. So now I try to find an ST path. Okay? There is no ST path. In fact, S can't reach anything. Right? S has no out edges. So I terminate. And then I halt with the current flow as my max flow. So I'll say, this is what I return. Okay? So that's the algorithm. So, does this algorithm terminate? Or what's the algorithm's runtime, I guess is the real question. And why is it correct? The two important questions. Let's first talk about runtime. So runtime it turns out you have to be careful about specifically what the input looks like, because it turns out in general, this algorithm does not necessarily terminate. So the original Ford-Fulkerson paper demonstrated a counterexample, a graph with 10 vertices and 48 edges, where the algorithm does not terminate. It just goes on forever. Later in the 90s, in 95, Zwick came up with an even smaller counterexample. For him, n was equal to 6, n was equal to 8, and he showed that on his example, Ford-Fulkerson does not terminate. And he also showed that his example is the smallest possible. There is no graph smaller than n equals 6, m equals 8, where Ford-Fulkerson doesn't terminate. But the key from both of these things is that their examples had capacities which were irrational. Right? So suppose you're allowed to tell your computer as input, this edge has capacity square root of 2. Or such, you have a way of representing capacities which are irrational as a string, let's say. You literally write square root of 2, right? SQRT2, as part of your input. And then you try to run this algorithm. Even if your computer has infinite precision arithmetic to deal with real numbers, you can prove that this thing will actually just go on forever. What about when the capacities are not irrational? What about when they're rational? What about when they're integers? Okay. Well, if they're integers, it definitely terminates. Right? Why does it definitely terminate? Because every time that you run an iteration where you push more flow along the residual graph, right? All the residual capacities, if they were originally integers, the residual capacities will still always be integers. Why? Because how do you form residual capacities? Right? You found a path in the previous iteration, you looked at the bottleneck edge, you looked at its capacity, which was an integer, right? And then you subtracted that residual capacity, you subtracted that bottleneck capacity from a bunch of other edges. So that's integer minus integer, which is still an integer. So it's definitely the case that throughout the entire process of Ford-Fulkerson, all the residual capacities remain integers. And if you're finding an ST path, that means you found a path. The bottleneck edge can't have capacity less than 1, right? 1 is the smallest positive integer, so definitely your bottleneck has capacity at least 1. So you're pushing capacity 1. You're pushing one more unit of flow from S to T in every iteration, right? If all capacities are integers, and let's say the max capacities at most capital U are integers, FF pushes at least one more unit of flow per iteration. What's the max flow you could possibly push? Well, S, the source S, has at most n minus 1 neighbors. Each one of those neighbors, to that neighbor, my capacity is at most U, capital U, which is the max capacity. So I have at most n minus 1 times U iterations. Right? Each iteration is a DFS, which takes linear time. So my total runtime cannot possibly be more than m plus n times n minus 1 times u. In fact, I have at most the value of f star iterations. Right? Where f star is, say, a maximum flow, every time I have an iteration, I'm pushing at least one more unit of flow. I can only do this at most val of f star times, because if I do it more, I'll push more than the max flow, which is not possible by definition of max flow. So my total runtime is O of m plus n, that's the time it takes to do a DFS in a residual graph, times the value of f star. And we said the value of f star is definitely at most, let's say, n minus 1 times the max capacity. You could ask the question, is this pessimistic? Maybe the runtime is actually a little bit better if I'm more careful about the analysis. In fact, I'm not being overly pessimistic. The runtime can actually be this bad. And let me draw an example for you. So consider the following graph. It's not that big of a graph. It only has 4 vertices and 5 edges. all these edges, this is S and this is T, all these edges have capacity U, except for the one going down, which has capacity 1. Okay. What might happen? Well, when I do a DFS from S to T in the residual graph, it might find this path. And then the bottleneck has capacity 1, so it's only going to push 1 unit of flow. Now I form the residual graph. What does the residual graph look like? So now I've fully exhausted the down edge that had capacity 1, so now the reverse edge is there, and the reverse edge has capacity 1. And then this has U minus 1, this has U minus 1, and this has U. And I also do have some reverse edges here with capacity 1. Now what might it find? Now it might find this path if I do a DFS. It might find this path. The bottleneck is again capacity 1. And then now I'll form a new residual graph. What does that look like? Now the edge goes down with capacity 1. I also have a reverse edge here with capacity 1, a reverse edge with capacity 1, etc. Reverse edge with capacity 1, reverse edge with capacity 1. But these are all U minus 1. And again, it might choose to use the middle edge and do this. And then the bottleneck has 1. So basically, what might end up happening with Ford-Fulkerson is, first you find this path, then the next time, let me draw that a little bit better. First you find this path, and then the next iteration, you find this path, and then the next iteration, you find this path. You just basically keep alternating. You either push down the middle edge or you push up the middle edge. And then you push down the middle edge, then you push up the middle edge. And you just keep alternating. Each time you're only allowed to push 1 because the middle edge is the bottleneck. So you're actually going to go on like this for something like roughly U iterations, or maybe 2 U iterations, even though the graph only has constant size. It only has 4 vertices and 5 edges, but you're spending time that depends on U. So again, just like knapsack, this is what's called a pseudo-polynomial runtime, right? Because it depends. This is not a polynomial time algorithm. Because specifying this input only takes log U bits to write U down, but my runtime doesn't depend on log U, my runtime depends on U. Okay? But, okay, it's not polynomial time, but if all the capacities are small, then, if all the capacities are like, say, 1 and 0, or constants, then it would be polynomial time, right? So it's not so bad unless you have really large capacities. I will say something about history for this problem. So Ford-Fulkerson is an older algorithm for this problem from the 50s. We do have better algorithms today. So here, let's say alg, and then the runtime. So we have Ford-Fulkerson from the 50s, which has runtime O of m plus n times the value of f star. It was observed by, or proven by, Edmonds and Karp as well as Dinitz. Edmonds and Karp. Karp is our own UC Berkeley Karp in the Eeks department here. That was in 1972, as well as Dinitz, who at the time was in Russia. That was in 1970. And what they showed is that both of them independently showed you can get runtime which is big O of n times m squared. Here, when I write down runtimes, I'll always assume that, let's say, m is at least n minus 1. If m is not at least n minus 1, it means that definitely there are some vertices that S can't even reach, okay? Which is kind of not so interesting. So pretend as a pre-processing step You just did a basic DFS from S, and anyone that S can't even reach, you just threw out of the graph because they're irrelevant. Okay? So from now on, I'll just pretend that M is at least n minus 1. So, and this algorithm is exactly Ford-Fulkerson, but where in each iteration, you find a residual ST path using specifically breadth-first search. What they showed is that if you don't use DFS, but instead you use BFS in every iteration, you can prove that the number of iterations you need is at most n times m. Each iteration of a BFS takes linear time, that's m, so in total your runtime is n times m squared. Dinitz, on the other hand, showed an alternative algorithm. It's not just Ford-Fulkerson with BFS, but a different algorithm that runs in time n squared times m, which is certainly better, because m could be as big as n squared. So he replaced an m with an n, which is always at least as good. And there was a long sequence of results. This is 50s, 70s. There was stuff after the 70s. And kind of where things stood for a very long time was an algorithm from 1998, which is due to Goldberg and Rao. And again, this is our own UC Berkeley faculty. This is Satish Rao, Professor Satish Rao, who's here in the EECS department right now. And the runtime here for this algorithm was big O of m times the min of root m and n to the 2/3 times log of n squared over m times log u. Let me make sure. I hope this is not in the way. But okay, so this is the dependence on u we like, right? U takes log u bits. The dependence on u is log u. We're happy. Log of n squared over m is always at most O of log n. But if it's a really dense graph, it could be a constant. The real action is here. It's m times the min of root m and n to the 2/3. Right? So root m is certainly always at most n, because m is at most n squared. So root m is at most, well, certainly this algorithm runs in time at most roughly m times n to the 2/3. But it could be better if it's a really sparse graph. For example, if m is on the order of n, it would be m root n. So that's where things stood for quite a while. But most recently, there's an algorithm due to Lee as well as Sidford in 2014. And that has runtime O of m times root n times log u. Right, so instead of n to the 2/3, it's n to the 1/2. Okay, great. So we saw what the Ford-Fulkerson algorithm is. We analyzed its runtime. Now all we have to do is talk about its correctness. So let's do that. So I need two lemmas. Lemma 1 is that any ST flow decomposes into a collection of at most m paths and cycles and lemma 2 is that if F is any flow such that it's not a max flow, such that val F is strictly less than the value of the max flow, then F star minus F. So literally I just mean this is a vector, take the difference vector, that's a vector, is a feasible flow in the residual graph. The residual graph GF. Okay. So those are the two lemmas. And I claim that, so we'll prove these lemmas, okay? We might have to defer some of the proofs of those lemmas to Thursday. But I claim that if you have these lemmas, that already implies that once you have them proven, it implies that Ford-Fulkerson is correct, okay? Why is that? So what's the problem? The problem is, I mean, we definitely know that throughout Ford-Fulkerson, we always are maintaining some kind of flow, some kind of feasible flow. And then at some point we terminate, okay? And when we terminate, we return some flow, okay? So that flow's value is certainly at most the max flow. It's not going to be bigger than the max flow because that contradicts the definition of max flow. But might it be strictly less than the max flow? Might it be the case that we get stuck at some f that's not optimal, but for some reason there's no valid ST path in the residual graph, so since we don't find a residual path, we just terminate. And by the way, I should mention just some jargon that I'll use, not just today, but we'll use in the class. Let me draw it here. Let me write it down here. These paths that we're finding in the residual graphs, like here we found this path, here we found this path, here we didn't find any path. These paths we're finding are usually called, jargon, augmenting paths. Okay, so augmenting path is just a jargon term. It means an ST path found in the residual graph. Right? And we call it that because we use it to augment the flow that we were currently maintaining. We augment the current flow by just adding it in. But such paths are called augmenting paths. Okay? So can it happen in Ford-Fulkerson that we get stuck? That even though we're at a flow that's not a max flow, for some reason there's no augmenting path in the residual graph. Can that happen? And I claim that because of these lemmas, the answer is no. Okay. Why? Well, we know that if we're at a flow that's not a max flow, its value is strictly less than the value of the max flow, then F star minus F is a feasible flow in GF. Right? That's what this lemma says. So it's a flow in some graph. What do we know about flows? Lemma 1 says flows decompose into collections of paths and cycles. Right? We saw that here, right? That flow, this flow right here, it decomposes into a collection of paths. Namely, there's this flow, there's this flow, and there's this flow. All of them are pushing 10. There are these three paths, right? That flow decomposes into a collection of three paths. Right? So that's what that lemma says. Any flow decomposes into a collection of at most m paths and cycles, where m is the number of edges in the graph. So we know that F star minus F is a feasible flow in the residual graph. That thing decomposes into a collection of paths, ST paths, and cycles. I should say ST paths in that lemma. What do cycles contribute to the value of a flow? Nothing, right? The value of flow depends on how much flow is flowing out of S. If you have a cycle, that doesn't contribute to the value. Let's say the definition, let's say the value of a flow is what's leaving S minus what's returning to S. So it's like what's actually leaving S. Okay? So cycles contribute nothing. Okay? Meanwhile, we know that, right? We know that the value, just because value is a linear operation, the value of F star minus F is equal to the value of F star minus the value of F, which is certainly strictly bigger than 0, because we said that this is not a max flow. So we have F star minus F. It has strictly positive value. It decomposes into paths and cycles. We know the cycles don't contribute anything to the value, so we can ignore them. So there are the paths. It has at least one path in its decomposition because it has positive value. So there's a path. That's what we're saying, right? There's a path. Okay? So you're not going to get stuck. There is an ST path. Okay? So as long as you're at a flow that's not a max flow, we know from lemma 2 and lemma 1 that there is an ST path with positive capacity in the residual graph. Okay? So that's one proof, and we'll come back to prove this, but I want to say there's also an alternate proof, and we'll see this next time, but I want to say it because I want you to be familiar with this concept. Okay? Because you might want to use it for homeworks in the exam. It's based on what's called the min ST cut. So definition, an alternate proof that Ford-Fulkerson is optimal. Definition, an ST cut is just a set of vertices. It's just a partition, let's say, of the vertices V into exactly two sets, capital S and capital T, such that little s is in capital S and little t is in capital T. And also I'll define the value of a cut. Or also let me not use val, let me use F. Another definition, the value of a cut f of s is just the total capacity going from S to T. It's just the total capacity going from S to T. So the total, okay, so val, actually, let me write val. So the capacity, let's say, sorry. The capacity of an ST cut, S, is U of S defined to be the sum over all edges E which go from S to T. So that's E intersect S cross T. So the first vertex in the edge is in capital S and the second is in capital T. So it goes from the capital S side to the capital T side of the capacity of that edge. So it's the total capacity leaving that cut. Okay? So for example, if I draw that graph again, I could take the cut that looks like this. Let's take this is a potential cut. So capital S is everything on this side, and capital T is everything on this side. This is an ST cut because S is in S and T is in T. What are the edges that are crossing the cut? This edge is crossing the cut, and this edge is crossing the cut. It's going from the S side to the T side. So the capacity of this cut is 20 plus 10, which is 30. That's not the only cut, right? Another cut would be I could say this is another cut and another valid ST cut, which is that S is on the same side with this vertex here. We said that before. This is called vertex A. So now what are the edges leaving this cut? This edge leaves the cut. This edge leaves, and this edge leaves the cut. Right? One side of the cut, one side of the edge is in S, the other side is in T. So the capacity of this cut is 40. Right? 10 plus 20 plus 10. So the min ST cut problem is find the ST cut of minimum capacity. Okay. And the theorem, which we'll see the proof of next time, is that max flow, the value of the max flow, is equal to the capacity of the min cut, the min ST cut. So S star, let's say, is the S side of the minimum ST cut. So max flow equals min cut. Okay, and the proof of and why does this, which by the way, as we're going to see next lecture as well, is somewhat predicted, not exactly predicted, but you'll see why not exactly, somewhat predicted by duality of LPs. Right? We saw that max flow is a linear program. So you could ask yourself, what's the dual of this linear program? And you can write down the dual. And it turns out that the dual looks a lot like the minimum ST cut problem. So strong duality tells you that the optima of these two things are equal. And why would this theorem imply, why would that be an alternate proof that Ford-Fulkerson is correct? And I claim the reason is, first of all, we're going to be able to prove that any ST cut's capacity is an upper bound on the best, just like duality, right? Weak duality. Right? We're trying to maximize something. We're trying to maximize the value of flow. We know that any solution to the primal has value at most the solution to something in the dual, because that's what the dual does, right? The dual LP gives you upper bounds on the best you could do in the primal. So we're going to show next time any ST cut's capacity gives you an upper bound on the max flow you could hope to achieve. And then we'll show you that actually Ford-Fulkerson gives you a flow whose value achieves the capacity of a certain cut. Which cut? Look at the last iteration. Look at the last iteration of Ford-Fulkerson. Okay? Where S can't reach T. And just make a definition. Here we'll make a definition. Look at the last iteration. That capital S is the set of all vertices V such that S can reach V in the final residual graph. Okay? And capital T is everything else. Since we know that in the final residual graph S can't reach T, that definitely means that little t will not be in S, which means it will be in the other side. It will be in capital T. And S can definitely reach itself via the empty path. So little s is definitely on the S side of the cut. So this is a valid ST cut. In this example, what can S reach? Well, in this example, S can't actually reach anything, right? Because it has no out edges. with positive residual capacity. So in this example, this is capital S, and that's capital T, is everything else. Okay? That's exactly that example right there. I mean, that's exactly that cut right there. Right? Little s is by itself, everything's on the other side. And we already saw, what's the capacity of that cut? It's 30. What's the value of the max flow in this graph? The max ST flow? It's also 30. Magic. Okay? We'll see next time it's not magic. We can actually prove why this is happening. It always happens. It's a theorem. It's a theorem that max flow is equal to min cut. And in fact, Ford-Fulkerson will give it to you. The final flow in Ford-Fulkerson will be a max flow. And if you define the cut, if you define an ST cut this way in the last iteration of Ford-Fulkerson, that cut will be a min ST cut. Okay? So this is another way of analyzing Ford-Fulkerson that simultaneously proves an interesting theorem about graphs, namely the max flow min cut theorem. This is usually called the max flow min cut theorem. Okay? So next time, we'll prove lemmas 1 and 2, which provides one proof of correctness of Ford-Fulkerson. And then we'll prove the max flow min cut theorem. Okay? And then we'll talk a little bit more about flow and its relationship to duality. And then finally, I'll give one application of flow. Okay? Again, anything that's on Thursday will not be covered by the midterm. But anything I said today, what is a flow? The fact that there's something called Ford-Fulkerson. How does it work? What is a residual graph? What is a residual capacity? The fact that there is this equality of max flow min cut. These are things you should know for the midterm. Okay? Even if you don't know how to prove this theorem, you should know that it's true. Okay? Okay. See you on Thursday.